This is problem 1367 on page 848. Cornhole is a game that requires you to toss beanbags through a hole in a wooden board. People with limited arm mobility often have difficulty enjoying this favorite tailgating activity. An adapted launching device attaches to a wheelchair so that points O and A are fixed. The device mimics an underhand throw by utilizing an elastic band to power the arm OC, which rotates about pin O. The elastic cord has an unstretched length of a foot and is attached to the fixed point A and at point B on the arm. Okay, I see what they're doing. Makes sense. The combined weight of the beanbag and holder at C is 4 pounds. And you can neglect the weight of rod OB. Should I understand all that? Yeah. A small clamp holds the beanbag, I think they mean beanbag, in the cup until release. Knowing that the starting position is 30 degrees from horizontal, as shown in the figure, determine the spring constant if the velocity of the beanbag is 31 feet per second when the bag is released at an angle of theta equals 45 degrees. Okay. The essential parts of this mechanism are O to A, and then the arm that pivots about O. So this is just ground. The fact that there's a wheelchair there is not really relevant to the problem. And somehow the beanbag is held in place. They say there's a clamp. What were you going to say?
So I think it's weird that to show he has an arm immobility, they put him in a wheelchair.
Oh.
It's
Good
like
point.
For your legs.
Good point. Yep. Didn't think about that. So then the second position where we're going to release the bag is at 45 degrees. And the bag is supposed to have a velocity of 31 feet per second. The weight of the beanbag and holder is 4 pounds. And I should put that here, I guess, because it's not the arm that's 4 pounds. And we know that the unstretched length, let's call it L free, because that's the terminology that's used for springs, or F sub L free, or whatever. The free length is 1 foot, and that free length is the free length of what is essentially a spring. Oh, that's not very good. A spring that's connected along this line between points A and, did they give us a name? Yeah, they give it a name, it's called B. Now this seems like a fairly complicated problem, but in fact it's really not too bad. If the beanbag is to have a speed of 31 feet per second when the bag is released, well guess what? So does that cup. So it doesn't matter that the beanbag is released once we get to this point. The cup's going to have some energy and it's going to keep going as well. Okay, so I don't know how it's released. That doesn't matter too much. All that matters is that we end up with that speed. Now, we're really using conservation of energy, and so the equation looks like this: T1 plus U12 equals T2, but I would recommend putting in a summation here. Why? Because the arm is in the vertical plane, there's going to be work done by gravity. There will also be work done by the spring that acts on the arm. How much work is done? Well, that simply depends on how much the spring is stretched once it reaches this new position. Okay? We'll have to figure all that out from geometry. They gave us some other information. For example, there's a 2-foot distance between O and B, and there's also, let's see, a 2-foot distance between O and A. There's further a 1-foot distance between C, well they gave us C1 and C2, between C1 and B, for example, or B2 and C2. So here's my approach. I'm going to figure out exactly how much the spring is stretched in the two positions and account for the spring energy. I'm also going to figure out how far it is from C1 down to C2 because C2 is lower than C1, right? Figure out how much work gravity does. Realize this starts from rest and needs a certain amount of kinetic energy at the end, okay? So let's, go ahead.
It's saying that the unstretched spring is from point A to B, but then it gets shorter.
I don't think it's from A to B. The unstretched length is 1 foot.
Well, it says in the example, points OA are fixed on, 1 foot is attached to the fixed point A and to B on the arm.
I understand, but it's saying two different things about this, the elastic cord. The elastic cord has an unstretched length of 1 foot. Let's put a period there. Okay. The elastic cord is also attached to fixed point A and to point B on the arm. You see, because the length of that cord varies as we go through the problem. And I don't know what the length is for any of these. We'll figure that out in a second. It may still have some stretching. I don't know. There could be a stop, right? So it runs into it and always releases at 45 degrees. We'll see. Any other questions or comments? Okay. So let's figure out the, let's write down the equation first, then we'll go back and pick all the pieces out that we need. So to figure out what gravity does, that's easy, negative W delta Y. It's always the same. It's just a matter of figuring out what delta Y is. We have to be careful and take positive Y in the upward direction opposite of gravity, but then the equation works out fine. And what about the spring energy? How do we account for that? Well, it's just the spring constant K divided by 2 times delta x2 squared minus delta x1 squared, where delta x1 and 2 are the stretch of the spring in the two positions. So for example, this is position 1, this is position 2, where we call it state 1 and state 2. So in state 1, the spring is much more stretched. Delta x1 is going to be huge, right? Versus state 2. And I've got these backwards. I should have 1 here and 2 here. Okay. But all I have to do is just copy down the work of the spring. There's the equation that's in the book. And then on the right-hand side, 1/2 mv squared. So that's simple, right? Now this spring and gravity have to accelerate the arm and, well, I guess the cup and the beanbag. They said the arm is massless. Why'd they say the arm is massless? If the arm had mass, then it would be rotating. It would be a mass that's rotating. We'd have to take into account the moment of inertia. But that's a body of size that's rotating. We'll get into that later in the course. For right now, we're just pretending that the arm has no rotational inertia. Okay. All right, so it looks like now I got to stop playing and actually start working. So let's go through the geometry and figure out how far delta y is. You see what I'm trying to figure out there? So delta y is going to be how far the arm comes down. So let's see, let's set up some triangles. In the initial position, we have something like this. We've got a 30-degree angle and a, let's see, from O all the way out to C would be a 3-foot side length. We've got 2 feet plus 1 foot. And I'll calculate this height on the side. How would I get that height? What do I need to use? 3 foot sine 30 degrees. Okay, sine of 30 degrees, if I remember right, is 1/2. So I think this is 1.5 feet. Am I right? Yep. Okay, so there's 1.5 feet. How about the other side? Well, on the other side, I've got a different kind of triangle. Well, not a different kind, it's also a right triangle. I've got a different triangle. Now I've got a 45-degree angle, and from O to C2 is still just 3 foot. So now this height would be 3 foot multiplied by sine 45 degrees. Sine of 45 degrees would be, what, 1 over root 2? So if we take 3 over root 2, what do we get for this height? 2.12. Thank you. The difference between those two looks to me like 0.62 feet. So delta y is 0.62 feet, is that right? No, it's not right. What's wrong with that? Delta y is a negative thing because it dropped down, right? The y height of point 2 is less than the y height of point 1. In other words, final smaller minus initial bigger gives us a negative number. So delta y is actually negative 0.62 feet. Okay? So that takes care of delta y. We got the weight, 4 pounds force. The question is the spring constant, if I remember right. So we'll have to rearrange the whole thing, but we'll do that in a minute. Delta x1, delta x2, let's figure that out next. Let me make a note up here, or over here, I guess. Delta y is negative 0.62 feet. That way we've got it, and I don't forget it. Then how much is the spring stretched? Well, that's a little bit different thing. There's a 2-foot side at 30 degrees from horizontal, and then the spring goes over to point A, which is a further 2 feet over. So I really need the length of this side. What do you suggest I do? Well, how about if we could figure out this angle, couldn't we? That angle is 180 minus 30 is 150 degrees. Could we use, let's see, I don't think we could use the law of sines. Let's see, it's either going to be law of sines, law of cosines. I'd probably just go over and draw it in SolidWorks and be done with it, but we'll figure it out geometrically, I guess. If that's 150 degrees, I notice that I've got two triangles that are the same. That means these two angles are the same. Sum of all interior angles for a triangle is 180 degrees. That means this must be 15. And 15 degrees on either side. Now that I've got that, I can use the law of sines. Let's see. So we'd have what? The side length that I want, let me call this LO for the operating length of the spring. LO divided by sine of 150 degrees equals 2 foot, say this side, divided by the sine of 15 degrees. So see how this angle, this 15-degree angle, goes with this side over here. So the operating length of the spring, when it's fully stretched, is equal to 2 foot times sine of 150 degrees divided by sine of 15 degrees. Okay. So go ahead and calculate, if you would, what the length of the spring is when it's completely stretched. What does that come out to?
3.86 feet.
How much?
3.86.
3.86 feet. Is that all? Okay. So what is the stretch of the spring in state 1? Well, the spring has, or the elastic band has, a relaxed length of 1 foot. So apparently the stretch of the spring, delta x1 initially, is 2.86 feet. I just subtract the free length, and that's how much has been stretched. Does that make sense to everybody? Any questions so far? Okay, so let's make a note that over here, in this position, delta x1 is 2.86 feet. How about delta x2? Well, that's a different geometry problem, so let's do it next. Work it next, I guess. So, in that case, we've got a triangle that looks like this. 2 foot on this side, 2 foot on this side, 45 degrees on this side. And the question is, what's the length of this side? So this is what I would call probably the installed length, but don't worry about installed versus operated versus free. Those are just names used for springs when you're designing springs. But you notice what we have here is an equilateral triangle. Of course, we can also note that these two angles have to be equal for the same reason as before. Let's see, so 45 from 180 is 135. Yeah, 135. 135 divided by 2 would be 50, plus 15 is 65, plus 2.5, 67.5 degrees. I'm thinking right? Okay. So how does that help us? Well, Li divided by sine of 45 degrees, these two are related, right? Equals 2 foot divided by sine of 67.5 degrees. So that means that the installed length, Li, must be equal to 2 foot times sine 45 over sine 67.5 degrees. Okay. So if you wouldn't mind calculating the installed length for me.
$1.53.
1.53, thank you. So how much is the spring stretched at the release point?
0.53.
3 feet. And now I think we've got everything that we need. Let's put it over here. Delta x2 equals 0.53 feet. I think we have everything we need in order to rearrange this equation and solve for k, which is I think what they needed, right? Spring constant. Yeah, spring constant. Okay. So what I would do is just write the right hand. Well, I guess I'd try to write it the way that would be least confusing to you. Let me do this. Equals, we'll write the right hand side, 1/2 mv squared. We'll move the gravitational work to the other side. It becomes positive w delta y. So that goes to the other side. And then we could write this term here, but we would need to move everything else to the other side. So we'd have to multiply both sides by 2. And we'd have to divide by delta x1 squared minus delta x2 squared. And that would give us k. So let's plug in the numbers and see what we get. K equals, well, let's see if we pull that 2 throughout. I guess let me perform a little bit of simplification. Pull the mass out. The 2's cancel, the mass came out, v squared, plus this would be mg, but I've pulled the mass out, so g delta y, but I've got a 2 inside of it. And I multiplied 3 by 2. Divided by delta x1 squared minus delta x2 squared. And I think we've got enough space to do this. So the mass is just 4 pounds mass. The velocity is 31 feet per second. That has to be squared, plus 2 times g, 32.2 feet per second squared, multiplied by delta y, where delta y is a negative 62 feet. Yep. Thank you. All divided by delta x1 squared, and that's 2.86 feet, minus delta x2 squared, 0.53 feet quantity squared. Let's check our units. Feet squared per second squared, feet squared per second squared. Numerator looks good. We've got pounds mass in there. Divided by feet squared. Now let's see. We're going to use up a pound mass foot per second squared from the numerator. To get pounds force out of it, we'll have to convert it. But that'll leave us with a foot in the numerator and feet squared in the denominator. So these will be pounds force per foot by the time we're done. So why don't you guys calculate what this is? Give me a number for K.
466.44.
Okay, and then we'll write down these. Does everybody agree with this number from what I've written down? Okay. Sounds like we got a couple people saying yes. The units that are left over are pounds mass, foot squared per second squared from this, divided by foot squared. You might say, well, let's just cancel the feet squared. Well, if you do that, you're going to have a spring constant in units of pounds mass per second squared. That's not what we prefer. So let me pull out one of the feet, that, and then realize what we need to do is multiply by 1 pound force per 32.2 pounds mass foot per second squared. What that will do for us is get rid of these pounds mass feet per second squared, and we'll be left with pounds force per foot. Okay? So just divide the number you had by 32.2.
14.49.
Everybody agree with that?
Yep.
There it is. So there's the spring constant we need for the elastic band in order to make this happen. Any questions?